What if I told you that this is what peak evolution looks like? That's right, 3.7 billion years of evolution has led to this. This knife-wielding, beach-raving decapod crustacean is the optimal life form. While this is a bit of a hyperbole, there is some truth to this. In this video, we'll talk about the process of carcinization, which is the phenomenon of evolution resulting in a crab form. This has apparently happened so many times that scientists had to create a word for it. So today we'll be talking about it. First things first, what exactly is carcinization? Well, it's more of a phenomenon than a theory, describing how the crab body plan has independently evolved multiple times. But what does crab body plan even mean? The crab body plan typically involves a wide, flat carapace, a tail tucked under the body, and fused plates on the bottom of the thorax. This configuration has emerged independently at least 5 different times within the infraorder Anomura, a group of crustaceans already quite similar to crabs. To understand why this happens, we need to talk about evolution. I'm sure we already all know how evolution by natural selection works, but I'll quickly go over it again if you didn't pay attention in class. So evolution by natural selection works through genetic mutations occurring from one generation to the next. If a mutation helps an organism survive and reproduce, it's more likely to be passed on. Over time, these beneficial traits will become more common in the population. So why does the crab body plan keep popping up? Well, put simply, it's because it works. A broad, flat carapace provides excellent protection, strong pincers are useful for defense and catching prey, and a tucked tail makes the body more compact and maneuverable. It's a versatile design that fits various ecological niches. This brings us to the concept of convergent evolution. Convergent evolution occurs when different species evolve similar traits independently, often because they face similar environmental challenges. Carcinization is a prime example of this. Just like how birds, bats, and butterflies all evolved wings separately, various crustaceans have evolved to look like crabs. Let's dive into the phylogeny, the evolutionary history, and relationships among species. The order Decapoda, which includes all crabs, lobsters, and shrimps, is a good starting point. Within Decapoda, the infraorders Anomura and Brachyura are of particular interest when discussing crabs. Anomura includes species like hermit crabs, king crabs, and porcelain crabs, many of which have undergone carcinization. However, Brachyura, commonly referred to as true crabs, represents a more specialized group within Decapoda. This group diverged from other decapods around 200 million years ago. Within Brachyura, there are several superfamilies, including the Carcinidae, Xanthoideae, and Portunoideae, each with unique adaptations. The Cancridae superfamily, for instance, includes the common edible crab, Cancer piguris, known for its robust claws and broad oval carapace. The Xanthoideae superfamily encompasses crabs like the European shore crab, Carcinus manus, which is highly adaptable and invasive. The Portunoideae superfamily features swimming crabs such as the blue crab, Calanectus sapidus, which have flattened hind legs adapted for swimming. That's right, crabs can swim. So think about that the next time you're swimming in the ocean. But how do lobsters compare to crabs? While both belong in the order of the Decapoda, their body plans are quite different. Lobsters typically have elongated bodies with a long, flexible tail used for swimming, and they are more adapted to a life of mobility in open waters. Crabs, on the other hand, have a compact body plan with a reduced and tucked tail, making them more suited for crawling and hiding in crevices. Lobsters use their tails to flick themselves backwards for quick escapes from predators. This tail, known as the pleon, is heavily muscled and allows for rapid movement. Crabs, with their tucked pleon, trade swimming efficiency for protection and stability, enabling them to maneuver through narrow spaces and defend themselves with their strong pincers. But what's actually driving these changes at a genetic level? Well, carcinization involves complex genetic mechanisms. Genes that control body segmentation, shell formation, and limb development are often at play. Mutations in these genes can lead to the development of crab-like form. Advanced genetic techniques help scientists identify these key mutations and understand how they contribute to the crab-like body plan. For instance, researchers have identified specific genes that regulate the development of the carapace and abdomen. One key gene is the Hox gene, which controls the body plan of an embryo along the head-tail axis. Mutations in Hox genes can result in the broad, flat carapace typical of crabs. Another important gene is the distal less gene, which influences limb formation. Changes in this gene can lead to the development of powerful pincers. Additionally, environmental factors also play a crucial role in carcinization. Crabs often live in environments where a compact, armored body is advantageous. For instance, rocky shorelines and coral reefs offer numerous hiding spots for crabs. A flat, rounded body makes it easy to squeeze into crevices, while strong pincers help in defense and foraging. In sandy environments, crabs benefit from a streamlined body that allows them to burrow quickly and avoid predators. The evolutionary pressures in these habitats have consistently favored the crab-like body plan, leading to its repeated emergence across different lineages. So now that we've talked about the general mechanisms of carcinization, it's important to clarify something. Only crustaceans can undergo carcinization, so no, we will not become crabs in a million years. Actually defining what a crab is a little more complicated than you'd think, and scientists aren't even at a consensus about what defines a crab. When we generally think of a crab, you probably go to a flat, rotund creature with little eyes and big claws. But not all creatures that follow this format are actually true crabs. So scientifically, crabs have to be under the Brachyura family. And these crabs have a highly reduced abdomen tucked under the thorax, which forms the compact body. And other creatures that we call colloquially crabs, like hermit crabs and king crabs, aren't actually true crabs, as they're part of the Anamura group, which has evolved to look like crabs, but aren't actually closely related to true crabs. Carcinization also isn't a process that we actually can see in real time. Like all forms of evolution, it's a process that occurs over millions of years. And scientists have noticed, based on how these groups are related to each other, one group of crustaceans evolved a flat and rotund body during the early Jurassic, and other groups evolved in a way that looks almost identical. Decapods have existed since at least the Devonian period, which happened about 400 million years ago. One of the first decapods we know of, Paleopolomian, had a body plan like that of a lobster, which was elongated and flexible. However, over the next 200 million years, the ancestors of true crabs adapted to the environmental conditions that led them to develop the crab body plan. Meanwhile, the ancestors of false crabs followed their lead. Most of the false crabs we know of belong to the Anamura group, which is the sister group to the Brachyura. This means that they're closest relatives within the decapod group. At some point, the common ancestors of these groups split, with the Brachyura lineage evolving into true crabs and the Anamura lineage evolving into various forms, including some that resemble crabs but are not true crabs. Some types of false crabs are the king crab, which evolved from a hermit crab ancestor, and the porcelain crab, which evolved from a squat lobster ancestor. These false crabs have undergone carcinization separately and independently of each other. So why did this actually happen? Since it occurred in so many different kinds of Anamuras independently, there must be some various environmental pressure that keeps leading to the same body form. The folding of the abdomen under the body is one major adaptation that likely provides protection against predators. In addition, it allows them to fit into tight spaces to protect them from possible predators. In the ancestor of king crabs, a shell protected the abdomen. However, over a million years, these ancestors adapted to protect their abdomens themselves. Interestingly, decarcinization, where crabs evolve away from the crab-like form, has also happened. In 2021, scientists found that decarcinization occurred at least 7 different times, including in the true crab lineage. Examples include the frog crab and extinct species Calichimera perplexa, which had a more elongated carapace and a protruding abdomen. Even though we like to joke about crabs being the final form, evolution is always in transition. Populations will continue to respond to changes in their environment and evolve on scales too small for us to observe in most cases. We just happen to live in a moment where multiple lineages have the crab form. So no, we will not become crabs in a million years, but maybe your favorite lobster species will adopt a crab-like body plan.